The science of solar storms. While those aging transformers sit vulnerable across our power grid, a cosmic drama is unfolding 93 million miles away that directly threatens their survival. Right now, as we approach the peak of the sun's activity cycle in 2025, massive storms are brewing on its surface that could send particles hurtling toward Earth faster than we can prepare. Particles capable of inducing electrical currents powerful enough to melt the very components keeping our civilization running. To understand this threat, we need to examine what's happening on our sun. The most violent events in our solar system are occurring constantly on the star we orbit. Solar flares are massive bursts of electromagnetic radiation spanning the entire spectrum: X-rays, gamma rays, radio waves, and visible light. These are enormous events. The largest solar flares release energy equivalent to billions of hydrogen bombs detonating simultaneously, making them the most energetic explosions in our entire solar system. When a solar flare erupts, electromagnetic radiation reaches Earth in just 8 minutes, traveling at the speed of light. Fortunately, our atmosphere and magnetic field shield us on the ground from the harmful radiation. Scientists classify solar flares based on intensity, using letters to denote their power. C-class flares are relatively minor. M-class flares are medium-strength events causing brief radio blackouts. And X-class flares pose the greatest concern. An X-class flare produces 10 times more power than an M-class and 100 times more than a C-class. Within the X category, the numbers increase with intensity. The most powerful flare ever detected was an X-28 in 2003, a measurement considered minimal because sensors monitoring it were overwhelmed by its strength. But the flare itself is merely the opening act. The second stage comes as a radiation storm, when solar eruptions accelerate charged particles into space at incredible velocities. Unlike electromagnetic radiation, these physical particles take longer to reach us, sometimes arriving in as little as 30 minutes after a flare. These high-speed particles pose particular dangers for orbital technology. They can penetrate satellite hardware, degrade solar panels, damage circuits, and create radiation hazards for astronauts. Even passengers on high-flying polar aircraft face increased radiation exposure during these events. The real peril begins with the third stage, the geomagnetic storm triggered by a coronal mass ejection, CME. These are the true monsters of space weather. A CME is essentially a vast bubble of superheated plasma erupting from the sun's outer atmosphere. These eruptions release billions of tons of solar material in a single explosive event, carrying intense magnetic fields along with them. Picture a gigantic bubble bursting from the sun, traveling through space at millions of miles per hour. When aimed at Earth, CMEs can reach us in as little as 15 hours, though slower ones might take several days. This gives some warning time, but not necessarily enough to protect vulnerable systems. When these magnetized plasma clouds collide with Earth's magnetic field, the interaction can devastate our technology. The danger lies in how CMEs induce powerful electrical currents that flow through available conductors, including power lines. These geomagnetically induced currents can overwhelm transformers, relays, and circuit breakers, triggering widespread blackouts. Additionally, CMEs heat Earth's upper atmosphere, causing expansion. This increased atmospheric drag slows satellites, potentially causing altitude loss and complete failure. What makes our situation concerning is the cyclical nature of solar activity. The sun follows an approximately 11-year cycle between periods of calm and intense activity. During solar maximum, the peak of this cycle, the sun's magnetic poles flip, transitioning from quiet to stormy. Sunspots, dark areas on the sun's surface marking magnetically active regions, indicate this activity. These regions birth solar flares and CMEs. As we approach solar maximum around 2025, these active regions increase dramatically. Dr. Maria Chun, solar physicist at NASA's Goddard Space Flight Center, provides context. Based on what we're observing, the upcoming solar maximum could bring widespread disruptions unlike anything we've seen in recent history. The sun is showing activity patterns that suggest we could be in for a particularly active cycle. What makes CMEs so dangerous is their magnetic structure, Dr. Chin continues. When a CME's magnetic field aligns opposite to Earth's, it's like opening a door, allowing the CME to couple more effectively with our planet's field and induce stronger electrical currents on the ground. Our warning systems rely on satellites positioned between Earth and the Sun, known as Deep Space Climate Observatory, SCOV, located at the L1 Lagrange point about 1 million miles from Earth, provides crucial early detection of approaching CMEs. However, even with these advanced capabilities, the warning period remains short, typically only 15 to 60 minutes to implement protective measures after detection. The question isn't if a major solar storm will hit Earth, but when. The 2012 near miss, when a Carrington-level CME passed through Earth's orbit just a week after our planet had been in that position, reminds us of this ongoing threat. Grid collapse, the first domino. That 1989 Quebec blackout wasn't just a historical footnote. It was a preview of what's to come. What makes this event so significant is how quickly everything fell apart. In just 90 seconds, a geomagnetic storm only one-third the strength of the Carrington event collapsed Quebec's entire electrical grid, plunging 5 million people into darkness for 9 hours. When solar storms strike Earth, they create powerful electrical currents in our power lines that overwhelm the system. Every mile of transmission line functions as a giant antenna, collecting and channeling these geomagnetically induced currents, or GICs, directly into the heart of our power infrastructure. When a coronal mass ejection reaches Earth, it interacts with our planet's magnetic field, creating rapid fluctuations. These fluctuations generate electric fields in the Earth's surface. Long conductors, like our extensive network of power lines, provide a perfect pathway for these currents to flow. The most vulnerable components are the massive high-voltage transformers forming the backbone of our transmission system. These transformers operate within tight parameters, but when GICs introduce DC bias, they begin to saturate, leading to harmonics, overheating, and eventual failure. The alarming aspect is how quickly this happens in a cascading sequence across interconnected systems. The 1989 Quebec blackout demonstrates this vulnerability with sobering clarity. The storm that hit that March morning wasn't exceptionally powerful by solar standards, yet it still managed to take down an entire regional grid instantly and damaged a massive transformer at the Salem nuclear plant in New Jersey. Had the storm been stronger or hit a slightly different location, we would be discussing a much larger disaster. The Quebec event was essentially a wake-up call, says Power Systems engineer Dr. James Chun. The circuit breakers tripped throughout the system as a protective measure, but not before damage had already occurred. In a stronger storm, these protective measures might not activate quickly enough to prevent catastrophic transformer failures. What makes transformers so critical is their function and the logistical nightmare of replacing them. Each high-voltage transformer is custom-built for its specific location in the grid, weighing hundreds of tons and costing millions of dollars. Replacement transformers typically take between 12 to 18 months to manufacture and transport, and that's under normal circumstances, not during a widespread emergency. Now, imagine dozens or even hundreds of these transformers failing simultaneously across the continent. A 2014 congressional report found that if more than 8 transformers in the United States were destroyed at the same time, the entire grid system would collapse. This cascading failure is not an isolated risk, but a systemic vulnerability that would spread like a contagion through the interconnected network. The mechanics of this cascade are particularly troubling. When one section of the grid goes down, the power it was handling must be rerouted through remaining lines. This places additional stress on the surviving components, potentially pushing them beyond their operational limits. As more components fail, the cycle accelerates until the entire system collapses. Using satellite night imagery, we can visualize how such a blackout would progress. Initially, major transmission hubs would go dark as primary transformers fail. Then, like a spreading ink stain, The darkness would expand outward along transmission corridors. Within hours, entire regions would lose power. Within a day, continental-scale blackouts could occur, with only isolated pockets of electricity remaining where local microgrids might have protection or generation capacity. Picture a sprawling metropolis suddenly silent, its skyline an empty void against the night sky, millions of people trapped in a darkness with no foreseeable end. The recovery timeline for such an event is perhaps the most concerning aspect. With manufacturing delays for custom transformers stretching beyond a year, and with potentially hundreds needing replacement simultaneously, full restoration could take years. The limited manufacturing capacity worldwide creates a bottleneck that no amount of emergency funding can quickly overcome. Grid simulation models run by national laboratories have confirmed these vulnerabilities. One simulation showed that a Carrington-level event could leave more than 130 million Americans without power for months to years, depending on how many transformers were permanently damaged. The economic impact would be catastrophic. Prolonged outages would trigger economic losses exceeding trillions of dollars. Modern manufacturing, food distribution, healthcare, and almost every sector of the economy depend on reliable electricity. Without it, supply chains collapse within days. Some utilities have begun implementing protective measures, such as installing blocking devices that can prevent GICs from flowing through transformers. These relatively inexpensive devices can significantly reduce vulnerability. However, implementation across the entire grid remains incomplete. For individual communities, the most vulnerable are those near the ends of long transmission lines and those in regions with high-resistance geology. Ironically, some of our most developed regions sit in these high-risk zones. During such a prolonged outage, water systems would fail without electrical pumps. Fuel couldn't be pumped at gas stations. Home heating and cooling systems would stop functioning. Food refrigeration would become impossible at scale. Medical devices requiring power would become useless without backup generation, which itself would eventually run out of fuel. Modern telecommunications would collapse. One communications blackout. Modern telecommunications wouldn't just collapse. They would vanish into digital silence. In an age where we take instant global communication for granted, imagine waking up to find that every satellite above you has effectively gone blind. Every cell tower stands mute, and the World Wide Web has unraveled. What happens when there's absolutely no way to call for help? Our telecommunications infrastructure represents the most vulnerable and least protected system in our technological ecosystem. Unlike power grids, with some hardening against electromagnetic pulses, our orbital communications network floats exposed in space, directly in the path of solar radiation. During a Carrington-level event, these systems become the first casualties in a cascade of technological failures. Solar storms deliver a devastating blow to satellites through charged particles damaging sensitive electronics and atmospheric expansion creating drag that can send them plummeting toward Earth. The results are catastrophic for our connected world. The communications blackout would be nearly instantaneous, explains Dr. Samantha Torres, who has spent decades studying telecommunications vulnerabilities. Within hours of a major solar event, we'd see widespread satellite failures across multiple systems and orbits. The redundancies we've built into our networks assume localized failures, not simultaneous global disruption. Picture a family in a medical emergency, frantically trying to call 911. The phone shows no signal. They rush to neighbors, finding every device equally silent. This scenario would unfold millions of times across the globe, like countless voices crying out into a void where no one can hear. Navigation systems collapse first. The GPS satellite constellation that guides nearly all modern transportation goes dark. Commercial airliners lose their primary navigation tools mid-flight. While larger aircraft maintain backup inertial systems, these drift in accuracy over time. Smaller aircraft essentially fly blind. Air traffic control loses precise tracking capability, forcing emergency protocols that dramatically reduce flight operations. Maritime shipping, carrying 90% of global goods, faces similar paralysis. Modern vessels navigate almost exclusively by GPS, with traditional celestial navigation skills now rare. Ships shelter in place or navigate by basic compass, essentially drifting back to 19th century capabilities while carrying 21st century cargo loads. Every day, transportation transforms overnight. Ride-sharing services cease functioning. Delivery drivers cannot locate addresses. Sophisticated logistics networks that optimize shipping routes collapse like a house of cards in a windstorm. The internet itself faces what experts call an internet apocalypse. Submarine cables carrying data between continents experience geomagnetically induced currents, potentially damaging repeaters and amplifiers maintaining signal strength. A Carrington-level event could cause widespread internet outages lasting weeks or even months, warns Dr. Torres, her voice carrying the gravity of someone who understands the full implications. The currents induced in cables could prevent servers from connecting, severing the digital nervous system of our global society. The United Kingdom government lists adverse space weather as one of the most serious natural hazards in its national risk register, alongside pandemic disease and major flooding. This represents concrete planning for national security organizations worldwide. The timing proves cruelly ironic. When emergency coordination becomes most critical, the systems designed for emergency response vanish. Police, fire, and ambulance services dependent on cellular networks and GPS face dramatically increased response times, particularly in rural areas with fewer visual landmarks. Hospitals already struggling with power outages lose access to medical records, telemedicine capabilities, and coordination with other facilities. Medical supply chains break down without digital coordination, leaving healthcare providers increasingly isolated as the crisis deepens. Even understanding what's happening becomes difficult. Weather forecasting degrades without satellite data. Emergency broadcasts reach fewer people as devices fail and radio stations go off-air from power outages. Backup systems provide limited protection. Telecommunications emergency generators typically last 24 to 72 hours, assuming fuel delivery remains possible. Satellite phones, often considered the ultimate backup, prove equally vulnerable to the same solar radiation affecting other systems. Military communications and detection systems face severe degradation, potentially creating strategic vulnerabilities in national defense. Modern precision agriculture relying on GPS-guided equipment falters, impacting food production when supply chains already face disruption. The scale of vulnerability is staggering, with over 1,700 active satellites orbiting Earth. A major solar storm could damage hundreds simultaneously. Unlike ground infrastructure, damaged satellites cannot be repaired, only replaced, a process requiring years. Current detection systems offer as little as 15 to 30 minutes of warning before a coronal mass ejection strikes Earth, barely enough time for basic protective measures. This timeline transforms theoretical risks into practical impossibilities for meaningful, last-minute preparation. Perhaps most concerning is how few understand these vulnerabilities. In an era where the cloud symbolizes reliability, the fragility of our digital infrastructure remains largely invisible. The satellites overhead, undersea cables, and server farms processing our data exist in physical space, vulnerable to physical disruption from a sun that has no regard for our technological dependencies. Economic